Swayam Prabha. Digital India. Educated India.
Carbon storage utilization, capture and utilization first. So this is the fourth session, so we are about halfway into the course. We'll try and keep to this schedule. I have divided up the classes into three subtopics: capture options, what are CDR technologies that we can use, what are storage options, and what is storage security. And we'll talk in more general terms. When we go into geologic sequestration, we will look at specific data on what do we do at various sites. So just to remind us all, the reason we are here is because we have, So this is the part that we are looking at if we don't do anything. If we do current policies, we are still aiming at 3 degrees centigrade rise above gust. And if we do all the pledges and everything comes true, we are looking at about 2.4 degrees. We think that we might be able to hit the 2 degrees target, but 1.5 is outside our reach. We should have gone somewhere here along that green line, and that window of opportunity has already passed. Yesterday, we looked at the status, a scorecard. This is a slightly more comprehensive way of looking at things. This is from Carbon Brief. That is a UK-based company, organization, and they pull in data from their databases all around Europe. What was interesting was this statement here. So what we're looking at is energy consumption in the oil equivalent and the mix of energy in renewables from wind, solar, geothermal, hydro, and nuclear, and this 3 being fossil fuels. What caught my attention was that India, this statement here right up top, India is the world's third largest emitter of greenhouse gases. And now the last 3 days we've been talking about this and we didn't get to this point at all. So I started digging a little bit more into data. I'm sorry I got a little bit sidetracked, but I think this is really interesting and key to how we look at data. That's one. How we narrow the data and plot them or make statements about data depending on which angle we are looking at. And so when we examine this a little bit more carefully, this is what I got. And you can download from this website, you can download all the data. This is country profile India. You can do it for other places. And there is a tab that says download the data that I used to make these statements and graphs. So I downloaded the data. The Git data source is out here, Cripps et al. 2024. And when I looked at the data, this is from 1970 until 2024. The solid line here, that's China. This dashed line is USA. This one here is India. And then the other two, this is EU, and out here we have Russia. And so this seemed a little bit odd, because the numbers were not adding up. Out here we have total over this span period, and China and USA seem to be about the same. So I compared with what we had been looking at. These were different data. Also from the same website, Carbon Brief. But these are historic emissions. That means this is over a longer span of time than 1970. 1970, countries were, India and China were trying already to catch up. And so when we are trying to compare, when we are trying to design our strategies, it's very, very critical to know what data we're using. Okay? This is the data I just showed you. This is the data we looked at yesterday or day before yesterday. The totals here are cumulative totals since we started counting. Most probably I'll have to go back and look to see when they started counting this time versus the time that we're looking at now. And so when we are examining how we strategize for decarbonization, for carbon management, what do we do for carbon management? It is very useful to have data that you are completely aware of and that are working in the same scheme as you need your design to be. You would have a very different strategy if you were looking at this set of curves or this set of curves or this one here. Same data, same organization. This is carbon brief. This one here is carbon brief as well. Okay. So, and the reason I'm pointing this out is when we design storage locations, we will use data. We will have to use data. We will do some calculations on how do we do geologic storage capacity. How do we design the sink for carbon dioxide? Those types of calculations require not these data, but similar types of data. And so if your data are, and it's a very simple thing, we'll play a little bit of game there where we will change the porosity, we'll change the thickness by 1 or 2 feet, porosity by 1%, and your storage capacity will change by thousands of tons, if not millions of tons, depending on how much of the material you have, how much of a storage capacity. So your storage capacity will change depending on the data that you use to make the plots. And so this was interesting in as much as the source of data matters, data confidence matters, errors in data matter. So when we do storage capacity for a reservoir, we have confidence limits on those to say we think it is has a capacity of 70 million tons plus minus 10 plus minus 5. That uncertainty comes from not knowing exactly what the area is of the target, not knowing what the thickness is exactly of the target, not knowing the porosity of the target. Okay, those are calculations that we do. Okay, so after that sidetrack, I went back to what I wanted to talk about, and this is the scorecard for India. Here are the emissions. There are in 2015 2.7 tons of carbon dioxide. Doesn't seem right either. Oh, per capita. Per capita emissions of 2.7 tons of carbon dioxide equivalent. And comparatively, this is what it looks like in 2015. It would be interesting to see what it looks like today. But this picture matches what we've been looking at. Here's India. Here's China. Here's US. This, before Brexit, these would have been together. You can dice things and say, okay, now suddenly they look much better. But if you were to put them together, this would be about 16 tons of carbon dioxide per capita, and that would be closer to what it is in US, right? So when we are looking at trying to examine what's going on, those numbers matter. These are the emissions for India, and again, this is from 2015, 2016, that's how far this goes. So we have fluorinated gases, NOx, methane, and other non-combustion building transport. So these are the sources of emissions. So when we're looking to capture, we're looking to say, where are we going to capture? What is easy to capture? Let's do that first. The pledge for Paris Agreement is here. This has since been updated. I have not compared the numbers right now, but I think we have them in yesterday's slides. It's easy to compare how much of a difference are we planning to make. What's most interesting is the energy production. Remember, we are trying to capture, right? So we're trying to say, which place are we going to capture from? This is our coal contribution. By far, the largest contribution to producing electricity comes from coal. And so, if we did nothing else, but took this coal, kept the coal as the source of electricity production, but designed a capture facility around that coal, the emissions would be much, much less, depending on how efficiently, even if it's not very efficient. Something at coal would make a much bigger impact than all of these things combined, just because we consume a large amount of coal. Right? We cannot say we'll cut off the coal, we're not going to use coal anymore, because these are not in abundance in India. We import oil and gas. So India is a net importer of oil and gas, so we cannot cut these. We can increase this part, but that will depend on capacity. We can decrease this part, but then we'll have to increase that proportionally. Remember, coal has a very high energy density. And so if we are replacing coal with any one of these alternative energies, we would have to do much more of effort to produce to get the same amount of energy for coal. So if we were to design capture facilities around coal plants, that would go a very long way. And I think that's something that we have ignored for a while, and we'll look at what strategies exist for replacing methane with coal, not to burn coal, but to use it for something else. Okay? Okay. So, and then of course I was curious, and so I compared it to US. This is energy production in US by major sources. What I didn't do, and I should have done, was to look at that amount and see if this is coal, this is natural gas, crude oil, natural gas liquids, nuclear, and renewables, right? So this is coal here. So we can take this amount of coal and convert that. This is the units are funky. This is in quadrillion BTU, whereas for India it's in terawatt hours. We can convert it. Here's the conversion factor. So if we take this, compare these guys, the numbers are very, very different. Right? So we are talking about scales of differences. But let's not spend too much time on that, because we want to get into capture and sequestration. Okay. So let's start with capture and sequestration part on what ecosystems exist. This is a very messy slide, but it tries to combine everything that we can do and everything and the consequences if we don't do that. So we have out here reforestation. If we let forests degrade, we remove forests, we will get into many more landslides and flooding. So these two would need to be replaced so that you are not degrading the soil out here, you are replanting. So this is by process of reforestation and afforestation. So this is green cover that we pledge to do. If you remember from yesterday's last slide, what India had pledged to do, one of the big points India had pledged to do was reforestation and afforestation. I think it was about 33% of increase in the amount of green cover. So that has a couple of benefits. One is of having green space. Second one is cleaning up the atmosphere, breathing space. Third one is to capture carbon dioxide, fix carbon dioxide. We'll look at another way where we can take the biologic waste, convert it into something useful. That's another way of capturing and storing carbon dioxide. So that's one part of it. What we can do is we can remove or replace the plant ecosystem with native species that thrive and grow in the area. So we have diverse type of plantations, and we are not encroaching one upon the other. The landslides, so this is from an experience that we had going in a ski resort, in a ski area. This was in the summer, and this was in Italy, and there was a big snow slide that had come in, an avalanche that got rid of most of the town downhill from the snow. And when they investigated why that was happening, it was because they had cut down most of the trees. People were much more affluent, and so in the summer, the grass was growing on the slopes. In early days, they would harvest the grass, the farmers. Once they became richer, they didn't find the need to harvest the grass anymore. That grass cover acted as a lubricant for snow to flow down. It dried up, became like dried, slippery, old grass. And so when snow cover landed on top of this, that whole thing slid down and rushed into the village. It was peak ski season, which means they had a lot of tourists there with a few deaths. That was a major catastrophe. We were talking to farmers that were in the area, and they said, yes, we cannot get our youth to go out and cut the grass, even if we pay them. So there are consequences to this sort of affluence that comes in from building a lot so that we can enjoy the slopes out here. The other part is to have a diversification of your stock and of the farming practices. Planting cash crops will solve the problem today, but will create issues as you go further. There are a number of programs out there to design smart cities, green cities that have concentrated population density with people living near where they work, so that you reduce the amount of commuting. In the West, this has been a sign of affluence that you don't need to live where you work, you can live further away. So it led to an urban sprawl. That urban sprawl has caused devastation by cutting down trees, by removing the ecosystem that used to be there. So now there is a big thrust with a lot of funding being spent into designing smart cities that are green cities, and so on. So you can, and this extends on to the oceans, where you have ocean acidification, and we'll look at schemes that are being promoted to remove ocean acidification by seeding, by adding material to it. And so there is a very big difference and effort that is required to go from where we are today to where we need to be. And it does not have to be all in technology. Part of it is a systematic and thorough design that allows us to create cities, to create livable environments that are honoring the fact that we need to store carbon dioxide. We need to capture carbon dioxide. Okay. So what do we mean when we say carbon capture? We've been talking about net zero. One of the terms that you should know in net zero is negative emissions technologies, NET. And you will find that as you go more deeper into the topic, as you start working more in this field, you will find this being used very often. What this means is that you change your process dramatically so that your emissions are reduced to minimal amounts. Those emissions can then be captured and stored or utilized so that the net effect in the atmosphere is zero. You're generating whatever you're generating, you're able to capture. What you cannot capture is what can be durably stored by natural processes. The natural carbon cycle can take over. So that's the part which is implied when we say we are developing net carbon capture, right? It requires obviously a complete transformation of what we are doing today. And so, for example, in the energy sector that generates about 3/4 of all greenhouse gas emissions, we would need to replace polluting coal, gas and oil powered power plants with energy from renewable sources. Or we would need to ensure that we are capturing all of the emissions from these power plants. And you will hear from faculty here who are working on different technologies on how much of the flue gas of the incoming materials is replaceable and capturable. If we're not doing that, then we are not looking at net technologies. If we're not doing net, we're not able to meet our goals. Right? So when we are designing things, we want to be mindful of where we're going. So what are some of the nets? We have, this is all plant-based. We have BECCS, that's biological bioenergy with carbon capture and storage. So we have fast-growing plants that are harvested, that are used to make biofuels, and the exhaust with the emissions are captured and stored underground. So that's your BECCS. We also have forestation, which is simple, you plant forests. Now, a couple of things that are critical here is you need land. To make a big difference, you need vast amounts of land that is available for planting. If we are doing BECCS or we are doing afforestation, reforestation, then we have to tweak. Remember, we said everything ties into one another. Then we have to tweak the agricultural growth in a way that we can still feed the population. We're not encroaching on agricultural land. So when you examine this carefully, we realize we don't have that much land to spend on BECCS. There are multiple use BECCS that are now being designed, or multi-layered BECCS, where you can plant in layers and then top everything off with solar cells or solar farms, so that you have a robust plant growth below that's used for BECCS, and on top you have energy from solar. We can look at direct air capture. This is air that is pretty much brought in like air conditioning, but you are funneling the air through membranes, some sort of filters, some sort of molecular sieves that capture your carbon dioxide selectively and let everything else pass. And then you renew them by releasing carbon dioxide, capture that, you can store it in the subsurface. Couple of these here. This is biochar. Biochar is the way, I think we'll talk about biochar. This is creating charcoal out of biological material, biologic waste that you can use. There is another scheme where you can promote enhanced weathering. You take rock mass, you crush it up. That rock mass then is spread on agricultural land, arable land, or in other places, that then captures carbon dioxide through the weathering process. The last one is ocean fertilization, where you spurt algal growth. That captures carbon dioxide on a vast quantity. These sort of technologies are being designed today. Some of them, like biochar, BECCS, forestation, are more mature. Ocean fertilization, direct air capture are low on the technology readiness level. This one is still in research phase. This one is in the test and implementation phase with pilot plants. It's not full scale implementation. So if we count up all of the previous one, you have afforestation, reforestation. We have biochar. This is an example of biochar. This is agricultural field that has been harvested. This is bio waste leftover. In most of Indian farming, this is burnt down, and you prepare the land, you till the land for the next crop. Burning of this crop or the spent crop releases a lot of emissions in the atmosphere. In this case, they're harvesting it, and you can see this thing cutting out here, going out here, collecting all of this material. This is then burnt in a low oxygen environment. It's pyrolyzed. As you pyrolyze it, it creates what's called charcoal. That charcoal is amazing for agricultural use because it has a large surface area. It has a very high water retention capacity. And so when you add it to soil, it enhances the moisture content in the soil. In places that have chronic water shortage, this becomes a very interesting technology. And so we are, this is still a very early stage. Technology readiness levels might be 3, 4. One of the big challenges is we do not know how deep you should bury it, how much you should use, how space should it be? Should it be mixed together? Should it be laid out in a layer? The char process is fairly well known. It's the usage that we don't know. There is a potential, if we do that, to remove 1.8, almost 2 gigatons of carbon. We have BECCS, the bioenergy with carbon capture storage. We have blue carbon, and there is a graphic that we'll look at in a minute to see what all of these imply for ocean type of carbon capture. So when we are designing all of this, we have a capture plant out here. And we need to have some sort of a transport mechanism. This can be by way of pipeline. It can be by way of as a compressed gas, either in liquid state, supercritical state, in some cases solid state. And the transport can be either through pipeline or by road or in ships. And that goes in either into usage or into storage. So essentially, we need to look at 3 major things. One is how do we capture? Second is how do we safely transport? And the third is how do we store? What are safe storage options? I will not discuss too much about the capture side, except when we look at mineral capture. And we'll talk about that part tomorrow, where we'll look at how do you use minerals to capture carbon dioxide, where does that capture happen, how does it happen, how much are we able to capture. We'll talk briefly a little bit about transport. What are the ways to transport, and what do we mean when we say we will transport as a solid? And then we'll talk a lot about the storage aspect. How do you design a storage site? What do you need? Okay, so again, a scorecard. Where do we need to be and where we are? Net. We are projected to decrease global greenhouse gas emissions, GHG emissions, by 2.6% by 2030. And this 2.6% is compared to 2019 levels. And these are based on the NDCs, the National Action Plans that were declared. If we want to be at 1.5 degrees, that needs to be at 43% by 2030. So our nets are not up to scale where we need to be. Okay? And the reason I'm pointing this out is because when we design things, for those of you who are designing capture facilities, you're designing ways to scale up, you need to know what your target should be. We need to go from 2.5% to 43% by 2030. That's 6 years from now. It's not far away, right? So that's really where we stand. That's where the scorecard is. This is for all the countries. This is from the United Nations Carbon Capture and Control Action Group or Working Group. Okay, so when we're looking at marine capture, there are multiple suggestions that have been made. Here's your biochar. We're taking all of this waste when the plants die away, we're taking that, hydrolyzing it with low oxygen, and using that to enrich the soil around here that promotes more growth. We can do enhanced weathering where we open up minerals here, increase the surface area by crushing the rock. When you increase the surface area, you have much more reactive surfaces that are exposed that can then capture carbon dioxide. Reforestation, direct air capture. We can remove carbon dioxide from the oceans here directly. There are other ways where people are promoting adding fertilization to oceans, taking biomass and letting it sink to the floor, and cultivating algae. Now, one thing, and then there is a scheme that says we can actually push carbon dioxide and make use of the density difference so that we can allow these lakes of carbon dioxide to form at various depths at the seafloor. Some of these, like the carbon dioxide lakes, are very early stage. The microalgae part is TRL maybe about 5 or 6. The work is being done. What remains to be examined is what will happen when this is conducted on a large scale. At the moment in oceans, if you have algal growth, that's a huge problem. I don't know how many of you remember the large infestation of algae, red algae, green algae, blue algae that have come in and shut down ocean beach resorts because they are toxic. So the thought here is to have algae that are not toxic, but yet capture enough carbon dioxide. And then you harvest it and either use it for biochar or for something else. So the reason I'm showing you all this is to say there are multiple ideas, multiple thoughts on how to solve the problem. It requires dedicated questioning to say, is this the way we want to go? Is this the right method, or is there something else? Okay, so when we separate out the methods, we can go into land-based CDRs. So carbon dioxide removal technologies, we can use changes to agriculture, forest, or land-based uses. So we have direct air capture that comes in here, accelerated weathering. This is already happening. So if you go from Pune to Hyderabad on the freeway, we have basalts that are being mined for building purposes. If you add water to it, right now that's not being used in a systematic manner. If you go through that cloud south of Pune, maybe 50, 60 kilometers, you come into this enhanced construction site, and the air quality, the particulate matter in the air increases. You can notice it as you go through it. The air is darker. You can feel when you're driving, you can feel the dust hitting your windshields. If you put water, you try to clean it, it just smears black across your windshield. So you know if you're breathing it in, it's not really that great. But those are small particles. Small particles means they have very high surface area. If there was a way to just capture that, and that's something which would be easy to do because it's already happening. Someone is crushing the rock for us. because they need building material. If you attach a suction to that, you now have very high surface area reactive materials that you can then use for accelerated weathering, either in the fields or as a way for building, low cost building purposes. We can also do, and there is afforestation, we talked about that, and we can combine that with biochar so that we take all of the dead material out, make biochar with it, and use that to enhance soils. When we look at geologic sequestration, we are examining formations where we can store about 1 kilometer at least in the subsurface. Often more. The reason we want to go deeper, there is a sweet spot, because as you go deeper, you have higher pressure, and so you cannot make use of the pressure differential as much. If you're too shallow, you're very close to the water table. So we want to be deep, but we don't want to be too deep. We have storage sites that go anywhere from about 1,000 meters, that's 3,000 feet, that's a bit shallow, but 6,000–7,000 feet, that's 2 kilometers, 3 kilometers is very common. Those are saline aquifers. That means that the groundwater, the water that is contained in these formations is too salty for human consumption. In the US, there is a requirement. If you want to use saline aquifers, the salinity needs to be above 10,000 parts per million. So NaCl equivalent. Your typical oceans will come in at around 3,500 parts per million, not 3.5 parts per million. So 3,500 parts per million. The requirement here is to go to 10,000. Above 10,000, it's not potable. Cannot be cleaned as easily. And so that is left for storage. We'll look at the reservoir that we are targeting in my project. And this is one of the biggest threats that we have, because we don't know if we will meet the 10,000 ppm TDS. We can go to depleted oil and gas fields. These are oil and gas fields that are not producing anymore. And so we can use them because we have depleted them to a point where they are under pressured from what they were when we started producing. So we have already a pressure buffer that we can use to store up and pump it back to the pressure where it was before oil and gas was produced. And so this gives us a larger storage capacity as compared to saline aquifers, because we know the amount of production we've had and the way we've produced. So the history is what we know. We need to know what it started with. Right? At the very least, it would be hydrostatic in starting producing, but then you would need lift. So we normally know what these pressures were, and we know when we abandoned them, we know what pressure they were at, either through measurements or through history matching of production. Yes, but excellent point. So we can use that pressure differential, right? If we are at, let's say we are at 6,000 feet, then our pore pressure, hydrostatic pore pressure, would be 3,000 psi, column of water. Let's say it's slightly overpressured, so we are at 3,500 psi. That 500 psi after we produce is the window of opportunity for us to pressurize it again over 10, 20 acres, thickness of 10 feet, maybe 20 feet, 100 feet is even better, and a porosity of 20%. We can do the math to say, and we'll do that in class next week. We will calculate how much of capacity do you get if you have a pressure differential of 500 psi to work with. Usually we don't have the luxury. Usually we have only a few hundred psi that we're working with. So this part is interesting, and if you look at the readiness, technology readiness level, here and here, it's a very high technology readiness because we've been doing oil and gas production for a long time. The drilling capabilities are well known. We can drill from two sides and make sure by geosteering, make sure that we meet somewhere in the subsurface. That is possible. We can target formations when that might be at 10,000 feet that are about 20 to 50 feet thick. So that technology exists, the drilling technology exists, the characterization and the mapping technology exists. What is challenging is the cementing technology. Cement is not meant to last for hundreds of years. We change cement out. Buildings don't last that long. When we drill for carbon dioxide, when we drill to produce, or drill to inject, and we'll look at well design, what that looks like. How do you plan it? You have a central core, that's usually steel, and then we cement on the side so that nothing else comes into the wellbore. We open and perforate in the zone we need to access. Steel corrodes with carbon dioxide. Over time, it starts to get pitted, it starts to get holes in it, and before you know it, you're leaking. Cement is not meant to last for long. We have currently, if we were to map, and that's another part which would be an easy fix, but easy, and that is to look at old wells. United States has a very long history of producing oil and gas, as does India. In Assam, for example, the production has started more than 100 years ago. Once you have drilled a well, you create an opening and you're producing because you have perforated so that oil can flow in and you out, or it comes out by itself. When the oil doesn't flow anymore, we need to leave it and go elsewhere, drill a new well. That old well is usually cemented up. Now remember, we said that these are 100-year-old wells. After 100 years, that cement, the technology has changed from 100 years ago. The cement itself has degraded. So we have a lot of wells that are leaking to the atmosphere. Usually it's in the form of methane. So there are maps, there are people who are using drones to map methane that's being emitted from old abandoned wells. We'll discuss this when we talk about the site that we are characterizing, because Colorado has a long history of oil and gas wells. Many of them, 100 years ago, no one cared. You plugged and abandoned. Today, plug and abandon means we pour cement down in the well, we shut it up, and everything is sealed. At least for the next 20 years, as long as the cement doesn't degrade. 50, 100 years from ago, A, the cement technology was not as good, if it was existent at all. B, the knowledge was not as good about what harms it would be causing. And people were dumping things down in the well bore, anywhere from old mattresses to broken down furniture parts to mud and earth. And so the sealing part is very questionable. In many cases, those wells are not mapped. It's very hard to know where do these old wells exist. So we have a colleague who does mapping with magnetic, because we need to locate them. The seismic doesn't work because these are point. They're not that large, they're not that big. The diameter might be, at the surface might be 20 inches. Wavelength, a seismic wavelength is tens of meters. And so 20 inches maximum at the top. As you go down, it goes down to about 6 inches. Finding those wells is like finding a needle in a haystack. So, yes. Right now, cement is the best thing we can do. Cement reinforced with something or some other material, I don't know. Who's the materials? We had one material scientist, a couple of them, right there. So, what's your name? Sorry? Soman. So, look, talk to Soman, right? They are the ones who will be inventing new material that we can put in the subsurface that will seal and remain, it will not get degraded by carbon dioxide. At the moment, we need materials that don't get attacked by acids, and we don't have adequate materials in the quantities we need. There are research thrusts that are going on to make cement more durable, make cement more less permeable, make it more self-sealing. So those are in progress, but sorry? Sure, if you can pour ceramic down a well, yes. So yes, those are some of the things. The thing is, if it's an oil and gas well, then cutting costs is the biggest thing because profit needs to be there. In the case of carbon dioxide, you don't have any money to work with, right? So it needs to be cheap, it needs to be sealing, it needs to be durable, it needs to be impervious. Those are some of the challenges. In old wells, and we'll talk about old wells next week. This is fascinating because we have challenges on how to find these wells. So if you were to think of going to Assam, right? When was the first well in Assam? 1886? Digboy, yeah. Digboy field. Anyone? Sorry? 87, 86, right? 1886, 1887. Let's say it had 50 years of production. Maybe let's give it 100 years. So 1987, no, 1987 is too long. I don't think it lasted. Let's say 1950, right? So 1950 wells are abandoned, and today we want to find them. And we want to know what the status is, how much are they leaking today. All of the production that's happening in Rajasthan, in Gujarat, there are enough abandoned wells that need to be mapped to see what their emissions potential, or how much are they emitting today. There are oil field leaks that are, for example, the heavy oil field Balol, right? Yeah, so Balol has a lot of oil around it. It's a heavy oil field, and that's being produced by heating up the oil so that it flows better. You increase the fluid mobility so you can produce it, and along the way that spills over onto the sides. So, if we were to make things slightly more efficient and get rid of the errors or the challenging parts, we would be very long along the way of mitigating